Hello and welcome everyone to the course titled An Advanced Non-Orthogonal Multiple Access Security Technique for Future Communication Networks. This is the first lecture of this course, and in this lecture we will be discussing about the introduction of communication security techniques. We will be talking about the motivation behind the NOMA technology. I will be also discussing the drawbacks in the conventional NOMA technology and how and why we want how we are improving this NOMA technology with our proposed new NOMA scheme. So just let's start with the need for secure communication in Industrial Revolution 4.0, such as in a smart city. Uh, the communication suffers from several security risks and drawbacks, such as a spoofer can manipulate the data and can cause accidents. A jammer can disrupt an undergoing communication and it can cause mishaps. Eavesdropper can hear or record your sensitive data and it can create or cause problems for you in terms of privacy issues. Uh, in a comprehensive smart city security structure, you expect several you expect several services in terms of data security, communication and network security, application security, connected devices security, cyber and physical convergence. And this is to achieve to achieve this perfect security structure. We need to have a very robust communication security scheme, and that has the capability to to combat and to work in parallel with the latest growing low complexity devices, which can work in synchronization with the low complexity devices. So the conventional schemes, the communication security techniques to secure the communication include cryptography. The cryptography based solutions require key sharing of data, which involves encryption, decryption, and this process requires a lot of information sharing, a lot of processing, computational processing, which might not be suitable for the future and the upcoming low complexity communication devices. So in order to fight with this drawback, and in order to overcome this drawback of the cryptography based techniques, the physical layer security has emerged as one of the most important security structures, which which has the ability to extract several characteristics of the channel, such as noise, fading, and randomness, and much more. It has the ability to read the statistics of the channel and design an efficient receiver based on the channel characteristics, which can result in much more fast communication, much more secure communication. So the I will be skipping this slide and I will be coming back to this slide. First, I will be talking about the limitations in the conventional NOMA scheme. In the conventional NOMA scheme, the existing physical layer security techniques for NOMA, they are either limited to the case of external eavesdropping, or they are based on cryptography based approaches that require key sharing, high processing, as I discussed in the previous slide. The conventional NOMA is most popularly known as the power domain NOMA, which suffers from the performance degradation such as successive interference cancellation, channel estimation errors, and SNI, signal to interference power noise ratio. I will be talking in detail about this second point in the next upcoming slide. So don't worry about these new terms such as successive interference cancellation and all. So the conventional NOMA was also adopted under the name MUST in release 13 of 3GPP for downlink transmission of two users. However, in recent release 17 of 3GPP, NOMA was not considered and it was excluded from the standard due to the lacking performance. So in this course, we will be designing a new NOMA scheme from scratch, the mathematical model plus the MATLAB design. Talking about the conventional power domain NOMA, in conventional power domain NOMA, there is a far user and there is a near user, for example. So the near user first subtracts the far user's signal and it decodes from the total signal and it decodes its own signal. So this subtraction of the far user signal this process is called as successive interference cancellation. And due to this excessive interference cancellation, there is a chance of internal eavesdropping, and there is high computation involved due to this excessive interference cancellation, which is not suitable for the low complexity communication models. Despite these drawbacks, NOMA has some promising features that it has high spectral efficiency, it has low latency, it has improved coverage, it can have massive connectivity, it can connect multiple users, and at the same time and it using the same frequency, and yeah, fairness and so on. Coming towards the proposed system model, this is the conventional power domain NOMA, where you have successive interference cancellation. And both the users are assigned with some sort of power levels. These power levels, for say the near user has the less power level, the far user has the more power level. So in the successive interference cancellation, we use these power levels to subtract the far users data and get this data out of the total signal. So the proposed system model consists of is illustrated in this figure. I will be talking about the proposed system model in the next upcoming lecture, and I will be giving a thorough explanation of this proposed system model. So see you guys in the upcoming lecture.